Hello chemists and welcome to today's lesson on alcohols. In this lesson we're going to be looking at the structure, properties and formation of alcohols. Before we begin, I'd like you to have a go at these starter questions here, which are based on alkenes that we looked at last lesson. So please pause the video here and then come back to check your answers. The general formula of alkenes is CnH2n, meaning that the number of hydrogens is double the number of carbons. Next we were asked to draw the following alkenes. Ethene has 2 carbons, and to show that it's an alkene we've included a carbon-to-carbon double covalent bond. Propene has 3 carbons. Remember that when we draw alkenes, only one of the bonds needs to be a double covalent bond, and we need to ensure that each carbon has a total of 4 bonds. This means on some carbons they won't have as many hydrogens as you're expecting. So this carbon here only has 2 hydrogens because it's part of the double bond, and this carbon here only has 1 hydrogen because it has a double bond on the left and a single bond on the right. In butene we have 4 carbons and we follow the same rules. And in pentene we have 5 carbons. Next up, we're asked to name the type of reaction that occurs when alkenes react with water and an acid catalyst, and we're asked to complete the reaction scheme, drawing whatever ethanol is in this box here. When we react an alkene with water in the presence of an acid catalyst, we produce an alcohol, and this type of reaction is called hydration. The product ethanol will look like this. You can see that the water molecule has actually added across the double bond. This hydrogen here has gone onto this carbon here. And the OH group left over has bonded onto the end carbon here. Hydration is an example of an addition reaction, which is the common type of reaction that alkenes undergo. The water in this reaction needs to be in the form of steam, and the acid catalyst can either be concentrated sulfuric or concentrated phosphoric acid catalysts. The test and result for alkenes is called bromine water, and it changes from orange to colourless if an alkene has been detected. Next we're asked about the type of reaction that occurs when an alkene reacts with hydrogen gas in the presence of a nickel catalyst at 60 degrees Celsius, and we need to complete the reaction scheme to draw this product here. The type of reaction an alkene undergoes when it reacts with hydrogen gas is called hydrogenation. Try not to get that confused with hydration, which is the addition of water. The hydrogen molecule again adds across the double bond because this is an example of an addition reaction. We get rid of the double bond in the process and form a single bond. So propane looks like this. You can see this carbon here now has an additional hydrogen, and this carbon here now has an additional hydrogen, and the double bond is no longer there, it's a single bond. You can also use a platinum catalyst for this reaction. This is an example of going from an unsaturated compound to a saturated compound, because it's unsaturated here as these carbons do not bond to the maximum number of hydrogens, whereas it's saturated here because all the carbons are bonded to the maximum number of hydrogens. Alkenes tend to burn with a smoky flame because they have a tendency to undergo incomplete combustion instead of complete combustion. Remember that there are 2 potential routes for incomplete combustion, one of which produces particulates of carbon, also known as soot, which produces smoke in this case, or the other of which produces carbon monoxide gas, which is toxic but difficult to detect because it's colourless and odourless. If we're getting smoke, then we must be undergoing the type of incomplete combustion that produces particulates of carbon, also known as soot. And remember that if you're doing this on a large scale, those particulates of carbon can actually contribute to an environmental issue called global dimming, also known as smog. Next up, we're asked to name the type of reaction that occurs when an alkene reacts with a halogen. Remember that the halogens are the group 7 diatomic molecules, so fluorine, chlorine, bromine and iodine, all with a little 2 written after their symbol. When an alkene reacts with a halogen, the type of reaction is called halogenation, but again this is a type of addition reaction like all the reactions of alkenes. The bromine molecule will add across the double bond, turning the double bond into a single bond. We'll put a bromine atom onto each one of the carbons either side of the double bond. So butene will become 1,2-dibromobutane. You don't need to be able to name that product, but you do need to be able to draw it. And you can also substitute that for chlorine, Cl2, or iodine, I2, or even fluorine, F2. The reason this thing is called 1,2-dibromobutane though is, first of all, it's 4 long, so it's bute. It's ane because all of the bonds are single bonds, so butane. The 1 and 2 refer to the positions of the bromine atoms. So if we labelled this carbon number 1 because it's at the start of the chain, then we've got a bromo on carbon number 1. We've also got a bromo on carbon number 2, bromo being the bromine atom. And it's dibromo because we've got 2 of them. So 1,2, 1,2, dibromobutane. Next up, in what process of the crude oil journey were alkenes first produced? Well, if we remember back to our crude oil journey, we started with extraction, then we carried out fractional distillation to separate the useful fractions. But then we had many long chains that were excess to demand. They weren't in high demand at all. So we carried out a process called cracking. And remember that cracking could produce a mixture of both alkenes and alkanes. There are many alkenes that occur naturally, but a lot of the alkenes that we use as feedstock for the chemical industry are actually the result of cracking. The purpose of cracking, as I just described, was to convert the long chain hydrocarbons by breaking their bonds to make those short chain hydrocarbons. And remember that short chain hydrocarbons were mainly in greater demand as they make better fuels. But a lot of short chains such as alkenes that are made are not used as fuels. They're used as feedstock, which are then used to produce different chemicals for the chemical industry. The 2 types of this process, that process being cracking, are steam cracking and catalytic cracking. Now we're going to have a look at alcohols. Now, alcohols are organic compounds because they're based on carbon and hydrogen atoms, like pretty much every compound you've seen in Unit 7 of AQA Chemistry called organic chemistry. Except alcohols have the OH functional group. This is known as the hydroxyl functional group, not to be confused with hydroxide, which is a negative ion that is present in alkalis. You can see that each one of these compounds has the OH functional group on it. What we're looking at here is something called the homologous series of alcohols. They're all alcohols because they all contain the OH functional group. And homologous series means that their structures are all the same, but they simply differ by CH2. So here I've got methanol because it's got 1 carbon, and its formula is CH3OH. You might be wondering why I didn't just call it CH4O. By writing its formula like this, we can clearly see the OH functional group and therefore identify it as an alcohol. If I differ this by CH2, I will get the next alcohol, ethanol. You can see that basically it's the same, but there's an extra CH2 here. It's eth, or eth, because it's 2 carbons long. And its formula shows this chunk here, C2H5, and then bolts the OH bit of the formula on the end to show that it's an alcohol. Next up, we've got propanol. Again, just an additional CH2. This is why it's part of the homologous series of alcohols. 4 carbons would give us butanol, and 5 carbons would give us pentanol. It's worth pointing out that this OH group could actually be on any position in the chain, but the name would change accordingly. At GCSE, we only look at alcohols where the OH group is on the end of the chain, and for reference, these are known as primary alcohols. Let's have a look at some of the uses of alcohols. The main use that you're probably familiar with, but hopefully not if you're a GCSE student, is the fact that alcohols are used in alcoholic drinks, predominantly this alcohol here, ethanol. You may also be aware that alcohols have antibacterial properties, which is why they're used in hand sanitizers. Finally, alcohols make excellent fuels because they readily undergo combustion reactions. Alcohols not only can be used as typical fuels, but they can also be formed from plants, so therefore they can work as biofuels. Let's have a look at some of the properties of alcohols. The first major property of alcohols is their readily undergoing combustion reactions, meaning that they burn very well. Let's have a look at what happens when we combust ethanol. To combust any fuel, you need to react it with oxygen, and all complete combustion reactions have the same products, irrespective of the fuel used. The products of this reaction will be, of course, carbon dioxide and water. The formula of ethanol, as we wrote it earlier, was C2H5OH. The formula of oxygen is always O2. The formula of carbon dioxide is CO2, and the formula of water is, of course, H2O. Now let's try to reapply some of the rules we learned last lesson to balance this equation. Let's start by counting the number of carbons, hydrogens and oxygens on the left-hand side, reactants, and the right-hand side, products of this reaction. We can see that there are 2 carbons on the left, and currently, because the equation is unbalanced, only 1 on the right. If we count the total number of hydrogens, be careful here, I have 5 and then a 6th here. So I have 6 on the left and only 2 on the right currently. Now let's count the number of oxygens. I have 1 here and 2 here, so a total of 3 on the left currently. I have 2 here and 1 here, so a total of 3 on the right currently. Whenever you're balancing combustion equations for organic compounds, compounds based on carbon and hydrogen, it's always good to follow a series of rules in this order. The number of carbon dioxides will be equal to the number of carbons in the fuel. So I have 2 carbons here, so I'll form 2 carbon dioxides. I can now change this number here to a 2. But in multiplying the number of carbon dioxides, I also multiplied the number of oxygens. So I'm going to need to rebalance for oxygen down here. I've now got 2 times 2, so 4, plus the 1, I've actually got 5 currently. The next stage in balancing these combustion equations is to look at the number of hydrogens on the left. I have 6 in total, and because each water molecule contains 2 hydrogens, I will always have half the number of waters as is the number of hydrogens on the left. So if I halve 6, I will get 3 waters. We've also multiplied the number of oxygen here again, so I'm going to need to rebalance. So 3 times 2 hydrogens gives me 6, but 3 times 1 oxygens plus the 2 times 2, which gives me 4, I've actually got a total of 7 oxygens on the right hand side now. Now, last time I told you simply to halve the number of oxygens on the right hand side and you would get the number of oxygens on the left. But this won't work in this instance because there's already an oxygen in the fuel. If you take the number of oxygens on the right hand side and take away 1 for this oxygen in the fuel here, we would have 6. Then halve it and you get the number of oxygens. So we've got 3 here. We can now see that this equation is balanced. 3 times 2 oxygens gives me 6, plus the 1 is 7, and that makes up the same number on the other side. When we use alcohols as fuels, if that alcohol comes from a plant, then we can consider the fuel to be carbon neutral. Ethanol, which is regularly used as a fuel, comes from sugarcane. The sugarcane absorbs CO2 as it photosynthesizes. I'm trying to balance here for the exact number of carbon dioxides over the entire process. That photosynthesis process will absorb CO2. 6 CO2s from the atmosphere plus 6 waters from the soil goes to form glucose C6H12O6 and it releases 6 oxygen molecules. We can take glucose from the sugarcane that is produced by photosynthesis and undergo the process of fermentation to produce ethanol. There is an enzyme inside yeast that actually can produce ethanol via anaerobic respiration. This process releases a small amount of CO2, but not the same amount that was absorbed. There's an equation for this process. The glucose is fed to the yeast and it produces 2 molecules of ethanol and 2 molecules of CO2. So currently in this process, we've absorbed 6 CO2, but 2 have been released. So we're still 4 absorbed overall, when we account for that released. Finally, if we were to take these two molecules of ethanol and combust them as a fuel, then it would release 4 CO2s. Let's have a look at that in terms of an equation. We take the two ethanol molecules that were produced by fermentation of the glucose molecule, which came from photosynthesis. We react it with 6 molecules of oxygen, and this will produce 4 CO2 and 6 H2O. You can see in total we've released 6 molecules of carbon dioxide in the production and then burning of the ethanol. And we absorbed 6 going in through photosynthesis. So therefore, alcohols can be described as carbon neutral if this is the method used to produce them, because it's a plant-based fuel that releases the same amount of CO2 or carbon dioxide due to combustion and other processes, the fermentation, as was absorbed during photosynthesis. In other words, the net CO2 in is equal to the net CO2 out. Let's have a look at another property of alcohols. Alcohols readily react with alkali metals to produce an alkaline solution. Take ethanol reacting with the alkali metal sodium. It will make a compound called sodium ethoxide, which is an alkaline solution. It will also produce hydrogen gas, because normally when alkali metals react with water or other substances, they can produce hydrogen gas. We could write a symbol equation for this. This is the ethanol. Sodium just has the symbol Na. This is the formula of the sodium ethoxide. You don't need to know that, but you do need to know the formula of hydrogen, H2. We could prove that the solution that's formed is alkaline using an indicator. You could drop in litmus paper, as is shown here, and it will turn blue. Alternatively, you could use something like universal indicator, which would turn purple. Remember that alkalis have high pHs, acids have low pHs. We could also test for this hydrogen gas that's formed here by dropping a lit splint into the area of gas, which would then give a squeaky pop result. There's a further property of alcohols which we're going to examine more next lesson, and that's that they can be reacted with oxidizing agents to form another class of compound called a carboxylic acid, which looks like this here. You can see the carboxylic acid has quite a lot in common with the alcohol in that it's got the OH group on this carbon. However, it's also got this double bonded oxygen here, and this whole group here makes it a carboxylic acid. Alcohols can be converted into the corresponding carboxylic acid using an oxidizing agent called potassium dichromate, which changes from orange to green during this process. But we're going to look at this reaction more next lesson, so don't worry about it too much today. So, please pause the video here and have a go at these tasks, and then come back to check your answers. The functional group we'll find on an alcohol is the OH or hydroxyl functional group. Next, we're asked to name and draw the first 5 alcohols. We should have got methanol, ethanol, propanol, butanol, and pentanol. The 3 main uses of alcohols are for alcoholic drinks, hand sanitizers, and biofuels. Next, we had to balance the combustion equations for the first 5 alcohols. 1 carbon in the fuel, so 1 CO2. You could have left that blank. 4 hydrogens overall here, so halve it, we'll get 2 waters. Next up, we can see that we've got 1, 2, 3, 4 oxygens on the right hand side, -1 is 3, then halve it, 1.5 oxygens. It's fine to write a half number in a balanced equation. 2 carbons in the fuel, so 2 CO2s. 6 hydrogens in total, so 3 waters. 4, 3, 7 oxygens in total on the right hand side, -1 is 6, I'm taking away 1 because of the oxygen in the fuel, half of 6 is 3. 3 carbons in the fuel, 3 CO2s. 8 hydrogens in total, halve it, 4 H2Os. 6 oxygens here, 4 oxygens here, 10 in total. Subtract 1 for the oxygen here, gives me 9. Half of 9 is 4.5. 4 carbons in the fuel, 4 carbon dioxides. 10 hydrogens in total, 5 waters. 4 times 2 gives me 8 oxygens here, plus the 5 gives me 13. 13 minus 1 is 12. Half of 12 is 6. 5 carbons in the fuel, 5 carbon dioxides. 12 hydrogens in total, 6 waters. 5 2s are 10, 6 1s are 6, 16 in total on the right hand side. Minus this 1 gives me 15, half of 15, 7.5. Next up, we're asked to explain why alcohols can be called carbon neutral fuels if they come from sugarcane. Remember that carbon neutral means that they're plant-based fuels, and the same amount of CO2 will be released when they're combusted or formed during the fermentation, as was absorbed during the initial photosynthesis process when it was a plant forming glucose. When alkalis react with alkali metals, what gas is formed, and what could you do to test for this gas? So, the gas that's formed when alcohols react with alkali metals is hydrogen gas, and the test for hydrogen gas is to insert a lit splint, which will give a squeaky pop result. Next up, we're asked what we could say about the pH of a solution formed when an alcohol reacts with an alkali metal. So remember, when an alcohol reacts with an alkali metal, an alkaline solution is formed, and alkalis have a high pH. So an alkaline solution is formed, giving a high pH, and to prove a high pH, we could do one of two things. We could either use a universal indicator, which will turn purple, or we could use litmus paper, which will turn blue. Now let's have a look at how we produce alcohols. There are two methods for producing ethanol in particular, which is the one we're going to focus on. The first method of producing ethanol we've already described partially. It's the fermentation of glucose which comes from sugarcane. This will produce ethanol. And the raw material for this process is sugarcane, which is a plant. And a key advantage of that is that it's a renewable process, in that plants can be regrown, so we're never going to run out of our raw material. The alternative method of producing ethanol is to hydrate ethene using steam, a key addition reaction that we looked at last lesson. The raw material for this process, however, is crude oil, which eventually is going to run out as it's a finite resource, so this is non-renewable. That's a key disadvantage of this process. Let's start by looking at the fermentation of glucose in more detail. We begin by taking sugarcane. A key advantage is that this is renewable as it's a plant. From the sugarcane, we will extract the glucose through several steps. The glucose will then undergo fermentation using yeast. There's a couple of equations to describe this process. Glucose gets fed to the yeast, and the enzymes inside the yeast act as a biological catalyst, speeding up the rate of reaction by lowering the activation energy. This produces carbon dioxide, and it also produces the ethanol that we desire as a product. And we can use symbol equations to describe the same reaction. The fermentation process is a batch process, as can be seen in this image here. These are fermentation reactors. Essentially, the glucose and the yeast get fed into these reactors in a solution with water, and it gets left in there for about 3 days to ferment. Batch processes are kind of irritating because they're slow and they have high staffing costs. However, because it's using an organism, yeast, it occurs at relatively low temperatures of 30 to 40 degrees Celsius, which are the optimum temperatures for the yeast enzyme to operate. This will use less energy overall, but a key disadvantage of this process is it only produces 15% ethanol solution. In other words, the solution you get out of this fermentation reactor is not pure ethanol. So if you're intending to use that ethanol as a fuel, you're not going to be able to use it because it's contaminated with 85% water. This is a limitation of the process in the fact that the yeast organism cannot survive in solutions that are higher than 15% ethanol. So therefore, after the ethanol 15% solution has been produced, it needs to undergo distillation, which is going to require more energy. Eventually, after the distillation, you will get pure ethanol. Next up, let's have a look at the hydration of ethene method of producing ethanol. First, we take crude oil, but crude oil needs to be processed. So, we're first going to carry out fractional distillation to separate out the useful fractions of crude oil. Remember that the short chains will probably straightforward be used as fuels. The fractional distillation process uses quite a lot of heat energy. Next up, the long chains that are in excess supply and low demand will undergo cracking, which again uses lots of heat energy. Remember that cracking produces a mixture of alkenes and alkanes. Some of those alkenes will be ethene, which will probably undergo a further distillation step before getting pure ethene. The ethene then undergoes hydration with steam and an acid catalyst, and this will produce pure ethanol straight away, so the solution you'll get is 100% ethanol with no further processes required. Here's an overview of that process which we've seen before. It's an addition reaction, so the water molecule adds across the double bond, with one of the hydrogens going here and the OH going on the other carbon, and the removal of the double bond changing it into a single bond. Now, the hydration process uses quite high temperatures, as do all the steps leading up to it, so it uses quite a lot of heat energy. However, this is a continuous process instead of being a batch process, so it occurs much more quickly and has lower staffing costs because it's constantly running and you don't need to keep filling and emptying big fermentation tanks. So please pause the video and then have a go at these review questions. Right then, so the two methods of producing alcohols and the raw material for each process are fermentation of glucose using yeast and hydration of ethene using steam. And the raw material, apologies, I didn't put it on the slide. The raw material for fermentation of glucose using yeast is sugarcane, which is a plant, and the raw material for the hydration of ethene using steam is crude oil. The part of yeast which converts glucose to ethanol is the yeast enzyme. The word equation for the conversion of glucose to ethanol via fermentation is glucose goes to form carbon dioxide plus ethanol. Next up, we're asked how we could test for the carbon dioxide produced by fermentation. If you bubble the gas through lime water, then the lime water will change from colourless to cloudy if carbon dioxide has been detected. Next up, we're asked to complete the comparison of both methods of producing ethanol. So we need to compare fermentation of glucose using yeast with hydration of ethene using steam. So we've first got to name the raw material and comment on the sustainability of that raw material. So the raw material for fermentation of glucose using yeast is sugarcane, which is a plant. And this is a renewable raw material because it can be regrown. For the hydration of ethene using steam, our raw material is crude oil, which is non-renewable. Next up, we need to comment on the manufacturing processes, advantages and disadvantages. So remember that the fermentation of glucose using yeast uses a batch process. So the reactor or fermentation reactor gets filled and emptied every couple of days. So it's quite slow and requires staff to do that. But because this reaction occurs at lower temperatures of 30 to 40 degrees, less heat energy is required. Whereas for the hydration of ethene using steam, we first needed to fractionally distill the crude oil and then undergo cracking, which both used quite a lot of heat energy. But the overall process that directly forms ethanol was a continuous process, the hydration of ethene. So it was much faster and had lower staffing costs, but again used quite a lot of heat energy. It's always important to remember that the heat energy used for any of these processes likely comes from the combustion of fossil fuels inside a power plant. Next, let's discuss the quality of the product. So with the fermentation of glucose using yeast, remember that our product is only 15% ethanol, so if you wanted to use that ethanol as a fuel, it would require further distillation. However, that product is carbon neutral if used as a fuel, which is a key environmental advantage as it will not contribute to global warming. The quality of the product via hydration of ethene using steam is 100% ethanol. However, the product is not carbon neutral, therefore it will contribute to global warming. Thanks very much for watching this video. I hope you found the explanations clear. In the next video, we're going to be looking at carboxylic acids. So if you wanted to read ahead on that one, then you can. Thanks very much for watching. See you next time.